followed by synchronous motor. So let's we in this continuation of topic. So we'll discuss about the copper losses and different power stages in the synchronous motor, as well as the problems. Okay, so that we given to for exam sample problems. Okay, example problems is that we will not discuss. Just we given the problems only. Okay, now we'll going to the next topic. Okay, so these are the problems which are related to the power equations, and we are discussed about the full or torque, pulling torque. Okay, so different torque produced in the synchronous motor. So these are the related problems. Now we'll discuss the next continuation topic. So the next continuation. Okay, so let we next topic is the effect of excitation. Okay, so this is the effect of excitation, how it will be varied in the motor at load at constant temperature that we are. Okay, so here whenever the load, okay, so here synchronous motor, whatever the load is there, so that will doesn't change. Okay, so whatever the speed is there doesn't change whenever the load is applied. Okay, that's the main property of the synchronous motor. So here we are talking about the when synchronous motor is kept loading. Okay, so kept loading at the constant. Okay, so the input power drawn by the remain constant. Okay, whatever the if it is load is constant, the power drawn by the machine also will be constant. Okay, since the applied voltage, okay, whatever the applied voltage will given the input was not constant. Okay, if it is load, whatever the load is constant, similar the applied voltage will be constant. Then the power developed by the machine also will be constant. Okay, similarly the other components also will be losses also, and other active components will be constant. Okay, so when excitation is okay, let's talk about the excitation. Okay, here we having the three excitations. Okay, so that is over excitation, under excitation, okay, rated excitation. Okay, so depend upon the excitation. Okay, this excitation will be deal with that's be given to the whichever the rotor. Okay, so we will given to the rotor. Okay, for the rotor will you give the DC supply. That DC supply if it varies, the excitation is changes. So that excitation will causes the here and the EMF. Okay, that back EMF induced in the R rotor. Okay, that will be changes. So here if the as well as the this excitation changes, the load angle also, and okay, so here the load angle alpha is constant for constant. If the load is changes, okay, the load angle also will changes. Okay, here these are the resultant voltage that we are discussed previously, that's the ER and internal angle, and that the angle bit. Okay, so here whatever the angles, okay, these are the cases. Okay, if what are the excitation, okay, if in case, okay, when excitation is such that, so the back EMF is direct is equal to the supply voltage. Okay, at this case how it will be, okay, this is under loaded condition. Okay, so previously we discussed about the under no load condition. Okay, so under no load conditions we would consider the one is the as like the current and voltage are in phase at some cases. Okay, so the voltage is lagging, sorry, current is lagging. Another case is the current is lead by the voltage. Okay, so these cases for the under no load conditions, so that works. Now we will talk about the under loaded condition and adjusted that whatever the excitation is that. So here excitation such a way that we adjusted by means of the uh, this rheostat. Okay, so here we are using the rheostat for varying the this excitation. Okay, so by directly supply we are giving. Okay, so here by means of the rheostat only we vary the excitation. That excitation is in a such way that back EMF is directly equal to P. Okay, so here in this case this vector. Okay, so we'll see the these type of the vector. Okay, so here we can observe. Okay, so this is the as we discussed previously. So this will know that. So this is a power 0. Okay, so in case of the we discuss in the RMF production, so this for 0, 60, 120 degrees and 180 degrees. Okay. So here in case of light. Okay. Similarly, here this is also fixed. So this excitation is varies. Okay. So at this case, so here the voltage and vacuum. Okay. So voltage and current is maybe is equal to zero. V. Okay. Is equal to same. But due to the direction, okay, the direction will be different. Okay. So magnitude may be a zero, but the direction due to the vector difference will be there because so here the supply voltage here we are applying. Okay. The opposition that back is in the different direction. Okay. So that's why the both are in opposite direction. Okay. The due to the loaded condition, the current, okay, the current is always lag, okay, in the other. So if it is leading means at the if it is current is lead by the voltage at that condition it will act as a capacitance. So at that time we'll use it for the power factor currents. Okay. This is under the loaded condition we are. So next is the we are reduce the okay. So we are reduce the excitation for here voltage is supply voltage is high and vacuum is less. Okay. So EB less than V at this situation. So how it will? So motor is set to be under excitation condition. Okay. So this motor is set to be under excitation. So here resultant. Okay. So resultant EMF will be the clockwise such an angle is a constant. Okay. So here we can see the this one. So resultant, whatever the resultant is that it moves to. Okay, so previously it will be leak. Okay, so the clockwise direction it will be changed to one to other. Next, in the case of this is the in a such way that so under over excitation. Okay, so under over excitation means the battery whatever the supply voltage is there that will be less compared to the battery. At this condition, how it will be acting. Okay, so the resultant is the anti-clockwise direction. Okay, the resultant. Okay, so one thing we may remember. So we have the three conditions. Okay, so one is the rated, below rated, overrated. Okay, these we can see. So depend upon the excitation, these EB is equal to V, EB less than V, okay, EB greater than V. Okay, so these are the three conditions we are talking. So let's see the here the vector representation. So here we can see the in the anti-clockwise direction. Okay, so previously the clockwise direction move. Here in this case the anti-clock. So here we can observe the power factor. Okay, so we can see that the current is lead by the voltage. Okay, that is the thing we can say. So previously it is lag side. Okay, present it is leading. Okay, so that is the difference we can observe uh, in the vector. Okay, so whenever the representation takes place, that we need to see. Okay, next we'll talk about the unity power factor, that is EB slightly greater than V. Okay, so in the previous EB greater than V, but as well as so it is nearly equal to zero or not, just if it is a slightly greater than V at this situation, how it will be look like. So it will be look like means in this situation the voltage and current are in phase. Okay, the voltage and currents are in phase. So that we need to identify how it will be there. Okay, so remaining that is the direction. Okay, so we can see the resultant direction. So resultant direction will also will be changes to the clock. Okay, so here the effect of excitation we can observe. Okay, so this is the below rated and another is the under, over and unity power. Okay, so these are the four cases at a time we see how it will be changes we can observe. Here this is the lagging, here also lagging, okay, here leading and unity. Okay, so here we need to observe the most of the cases. First if we draw the supply voltage, then same magnet we can draw and then we can draw the one. So resultant. Okay, so based on that, if we draw the parallelogram, so we'll get the this. Okay, so then we have in the current direction. So we can see. So this is the current and this is the resultant. So these are the four cases we can. So depend upon the how the theta, internal angle, load angle, and power factor angle, how it will be changing, that we can see here. So EB is equal to V, EB less than V, EB greater than V, EB greater than slightly vary. Okay, that is a unity power factor that we can see here in the four cases we can. So these type of the question representation we to draw for some examinations came for 3 marks question. Okay, so only for this diagram. Okay, so if you practice the 2 or 3 times, but with analyzing, then it will be easy to understand, okay, and easy to remember. Next here, to talk about the silent features. So what are the features of the, so so magnitude of the armature current varies with the excitation, okay. So whatever the varies with the armature current, it will varies, and current the large values, both low and high values will be exact, okay. So in between the minimum values correspond to the certain excitation, okay, depend upon the values as you observed the previously here. So from this one, how you can observe the features that we are here mentioning. So here the same input, okay, for the same input, armature current varies with the more wide range of causes, power factor also will occur. So here we can observe the three power factors like the uh, LPF, UPF, okay, low power factor, unity power factor, okay, so leading power factor, okay, so leading, lagging, okay, so we can observe the three cases and under. So whenever the over excited, it will goes to the leading power factor. Under rated excited, it is act as a this, okay, so unit power factor. Under below rated, then will act as a lag factor, okay, depend upon the excitation, the power factor will vary. So these based upon these properties, the synchronous motor will use for the industrial purpose for power factor correction, okay. So we'll using for the application the power factor correction in the machine. So here when lagging power factor, that is under excitation cases. Okay, so if it is power factor unity, then it is a normal exit that we are talking. Okay, so if the power factor is decrease, or the increasing or decreasing, that is the with the in the excitation. Okay, if wanted to change the power factor of the machine, then we need to control the that DC excitation which you are using for the giving for the road. Okay, here, let's talk about V curve. So here in the V curve, so why it is called the V curve and as the V curve inverted V curve means how it will be there. Okay, so whatever the graph will drawn, okay, the armature current plot against the excitation that will comes as the V. That's called the V curve. Okay, so another so that will the curves will look like as a V. That will called as a V curves. Okay, so the armature current versus excitation. Okay. So these are the both are the current. So IA versus IF. So different load, if we increasing the load and how will be done. Okay. If you observe. So IA versus IF, if you observe, so load will be increasing and again if excitation varies, that will look like it. So different variation. Okay. So here we can update the curves as a V curves. Due to this shape, it will be called as a V. So here V curves synchronous motor shows you how this IA. Okay, so armature current, where is the excitation for the same input. So here the V curves for no load, off load, and full load. Okay, so depend upon the load. So how it will be look like, we can see here. So these are the three situations. So here we can see this is the armature current and here is the field current. Okay. So this armature current and this is the field current which are giving the excitation. Okay. So if it excitation, okay, here we'll start the excitation from the 0 and up to the rated value. Again, if it increases, okay, how it will be varies. So here what will happen at the initial stage, okay, the current, whatever the armature. Okay, so for this one we will do the experiment. Okay, so in the synchronous mission, this practically we'll do in the experiment. Okay, one of the experiment will have in the AC motor. Okay, AC motors. Like here we'll take the IA and IF. Okay, so here what we'll do? So we will vary the excitation by means of the this rheostat. Okay, by means of here from the 0 to, if you vary the rheostat. Okay, from starting to 1. Okay, so here rheostat is act as a potential divider. Okay, here if where is this potential divider? So here we observe the per 0.1 how much current, per 0.2 0.4, like this we will take the up to the rate above rated. Okay, continuously we are increasing. Okay, at this stage how much current? Okay, so how much current we observed in the armature? Okay, so that will be taken here. Okay, so that current we will take, and based upon the 0.1 how much we will take it. Okay, for 0.2 how much, for 0.3 how much, okay, for 0.4 how much, for 0.5 how much current. Okay, so if it is current is increasing and decreasing, okay, like this we will adding the all the 5 will draw the one. Okay, this is for one load, means we are mostly depend upon. Okay, so without load applying one. Okay, after applying the load, what is that? Okay, if you are applying the half of the rate. Okay, so suppose here the load is nothing but here, so we will having the uh, this is the motor, and here we will see having the this uh, spring balance. Okay, so whatever the spring balance is, so without applying the spring balance load, so how much variation is there, that will find. Then if you apply the half of the load, okay, suppose if the rated machine of having the 21 amps, okay, then we apply the 10 amps rating. Okay, up to 10 amps rating, then what is the values are there? Okay, that will we will draw like this. Again, if you apply the up to 21 amp, so what is the values? Okay, that we can observe here. Okay, so these are the values you can observe. So this is the, it's called as a, it will look like as a V, so that's why called the V curves. Okay, so we will do the experiment. So in that one we'll take the different parameters. Okay, so next we'll come the inverted because, so same whatever the same experiment we'll do here, in that experiment only we will taking the readings. Okay, so based upon the readings, so we will draw the graph. Okay, so here we will draw the power factor. Okay, so we will take the graph between the power factor versus the load factor. Okay, so here under different load conditions, power factor versus against excitation. So here we will consider the same. Okay, so here IF, and here the power factor. Okay, 0.1, 0.2, 0.3 inches. So how it will be look like. So here you can see. So here at the different conditions, these will be varied. So how we can calculate the power factor means we can use the uh, our watt meter, okay, or power factor meter. Okay, so we can by means of the power factor meter or watt meter. So depending on three-phase watt meter or two individual single phase watt meters which are using. So based upon that we can get the this power factor, and we will plot the, okay. So in this case we will plot the that supply voltage, armature current, field current, or that is nothing but excitation, and watt. Okay, and here we'll take the power factor values, we'll calculate, and the speed, and this value. Okay, so and efficiency also if we can calculate, we can calculate. Okay, so different values we will consider, and suppose how much if you apply the load. Okay, so how much load is there? Okay, so based upon these values all thing we measure, and we'll draw the this. Okay, here uh, for our career, so we are having the two. Okay, that is the one is the uh, so here IF versus IA, if you draw means we'll get the V curve, and if you draw the power factor versus IF, we'll get the inverted V curves. Okay, that's the tip. So remaining will be, so one experiment will get the two graph. That is the difference. Okay. So next we'll talk about the synchronous mode. So how will we wait? So that will be so for from the inverter with the power factor is lagging and motor is under exit. Okay. When leading, then it is over exit. Means how it will be varies. Okay. So based upon the values, how it will changes. Okay. So that will be, we can observe from the excitation thing, potential divider varying, how it will can. Okay, next we'll talk about the synchronous condenser. Okay, in the synchronous condenser, as a condenser, okay, so before talking about the condenser, let's talk about the our fan. Okay, so fan having the one capacitor. Okay, so we'll call as a condenser, and cooler also having the fan. So this also works with the capacitor. So these will call as a condenser. So what we'll do? So whatever the current is starting purpose, we will using the this capacitor. Okay, here. So similarly, uh, not like the for starting purpose. Okay, so here the condenser. Okay, a condenser or capacitor. Okay, so a condenser or capacitor always draw leading current from the AC system. Okay, so condenser capacitor always draw the leading current from the okay. So depend upon, so we'll having the power. Okay, so power will having the, so we'll having the S plus Q. Okay, actual power, reactive power. Okay, that will get the apparent power. Okay, so that is will get it right. So similarly here, so we'll having the depend upon the power supply. So we'll draw the leading power. So here leading from that one getting the only leading current. So lagging current will, whenever the most of the loads are will having the practically what's called the, so first we'll if we talk about the loads, so we'll having the three types of loads. One is resistive load, another is the inductive load. Okay, so capacitor. Most of the loads are combined with the resistor and inductive. That's why most of the supply will take from lagging power factor only. Okay, so capacitor loadings are only used from the laboratory system. It's a practically, so not used in other. Okay, so that's why we're getting the only lagging power. If lagging power factor increases, what will happen? So the current drawn by the whatever the machinery is there, so it will draw the more current. Okay, due to the more current, more wastage. More wastage means more consumption. More consumption means power loss. Okay, so in this will continuously, due to the industries, what will happen? If lagging power factor increases continuously, so at that time, what will happen? So in the billing system, okay, so in the power distribution system and transmission, okay, so whatever depend upon the industry. So if it is a distribution, so in that billing, so based upon the their maintenance of the power factor, so they will get the that separate billing. Okay, so if lagging power factor is poor, okay, then we'll getting the more bill. Okay, so if it is you are there maintaining the leading, okay, so you nearly leading power factor, then we'll get the less bill. Okay, that will having the, because so to supply the that type of power, so they will have the more. Okay, that's why, so based upon the how much power factor they are maintaining, that's also billing will also change. Okay, so that's why they are used to try to maintain the near to leading. Okay, so here next coming to the, it is now the synchronous mode. Okay, now the synchronous could operated at unit power factor, lagging power factor, leading power. Okay, by, so how we can be changed? That is by means of the excitation. Okay, if excitation changes, back EMF changes. Back EMF changes means that will power also current drawn by the machine changes. If the current draw the machine changes means power factor changes. Okay, so here the ability of the synchronous mode. Okay, the ability of the synchronous to operate the leading power, okay? When how much excitation, that is over excited. Okay, so under over excitations only the leading power factor will take place. Under normal excitation doesn't happen. Okay, so it need to be over excited. Okay, so then not list the the power factor of the system. Okay, so the ability of the synchronous, okay, synchronous to operate leading power factor when overexcited is utilized in improving the power factor of the system. Okay, so what will happen if we give the motor for over excitation? So throughout the system, whatever the power supply we're getting from the, suppose here the laboratory and here we're using the synchronous motor, here all the AC motors are working. Okay, due to that, here whatever the lab is there for that lab, so the power factor is decreased. Okay, so we wanted to improve the power factor. So what we have to do? So we need to run the synchronous motor and up to the above excitation, that is over excitation, then all over the machinery. Okay, the current drawn by the machine will be reduced even though load is increases. Okay, and that is all the that is power factor of the system. Okay, that will be improved by the synchronous motor. Okay, next, so when synchronous motor is used to power factor improvement, then no mechanical load is occurred. Okay, so for only for we don't want using the for only improving the power factor means, then it's called as a synchronous condense. Okay, so only purpose of motor only running without no load means, then it is called as the synchronous condense. Okay, it draws the leading current and does the as act as a static condense. Static condense means as like capacitor it will work. Okay, so its name is called as a synchronous condenser. Okay, so this will be useful for installation where power factor is low. Okay, where is the power factor is, then if we install the synchronous motor and without applying the load, if we run the synchronous motor, then the whole of the system will be try to be in a try in leading. Okay, so power factor will be goes to the high. Okay, so at no load. Okay, and the one we call as the at no load condition. Okay, so synchronous motor operates at the here load angle should be there. Okay, and means VBR out of this like this. So when motor draws the leading current, so zero power factor conditions, that will be having the this variable K. Okay, so as it will be shows when act as a lagging current. Okay, so motor draws a lagging power current, then it will be as a variable index. Okay, so we can see the directions and this. So here next talk about the induction motor takes the lagging KVR. Okay, so as we discussed about the power triangle. Okay, so power triangle. So as we know that so power triangle. Okay, one side kW, one KVR, and as the kilo. Okay, so at that time, so here the in the power triangle, so we're getting the KVR, KV, and kilowatt. Okay, so an induction motor takes the lagging KVR from the supply and set to the air gap fix. Okay, suppose here we're having the this is the induction motor and we are giving the supply. So what will give it? It will take the how much current. Okay, whatever supply is that will give the and produce the a flux in the air gap. Okay, hence it operates in the lagging forward. So this will happen. What will happen? So due to the high amount of current, so what will happen? It will produce in the lagging power factor in the system. Okay. So when if we run the synchronous motor near to this induction motor, so it will reduce the care. Okay. So what will happen if it is over excited? So lagging the power factor is improved by the this synchronous motor, and here what will happen? So the KVR, okay, that will be reduces. Okay, in this way we can improve the power factor of the system. So if the over-excited synchronous motor connect to the parallel with the induction motor, okay. So what you are telling me, if a over-excited synchronous motor connect parallel with the induction motor, it supplies, okay, it supplies lagging KVR. Okay, as we may in this. Okay, if you run the parallel, then we will produce the lagging KVR. Okay, reactor power. Okay, so that will react to or you can observe. So distribution lines are relieved will complete supplying the lagging curve needed by the induction motor. Okay, okay, the supply lines have to handle the reduce KVA and reduce the current, so that we can tell. So here we'll having the here this leading better operation. Okay, so overall system, what will happen? This will be producing the efficiency. So if it is losses is reduced means the efficiency of the system also increases. So in induction motor, so still up in the same lagging power factor after the KVR. Okay. So if it combine the synchronous motor and induction motor, then we can observe the that improved power factor. Okay. That we can observe in the parallel or unit operation. Okay. That means. So this is the phasor diagram. You can see how it will be there for the if you run the machinery. Okay. So this is a problem related to the uh, induction motor and synchronous motor if parallel runs, and how it will be the where is the power factor. Okay, so this related. So next we'll talk about the dual purpose of synchron. Okay, so any factor is the induction motor fluorescent in common, and synchronous motor is a very two purpose. Okay, one is drive the mechanical load and correct the lagging power factor. Okay, so here these are the situations. We can see the if what is KW, KVA, KVR means that we can observe in from the uh, power triangle. So if you understand the power triangle, so what will be varies, then we can understand easily this one. Okay, so I'm not giving the in detail explanation. Just you may go through the in detail explanation about the this power triangle. Okay, so then we can understand easily. So because need to the do the problems, then only you can understand the kilowatt, kVA, kVR. Okay, so this will in the power triangle operations only you can understand. Okay, so these are the problems related to the power factor and all things. So you may go through the. Okay, so next topic, okay, we'll talk about the hunting. Okay, so hunting is caused due to the synchronous motor for driving varying the load. Okay, so if you apply the variable load for the mission, so that will cause the it will happen with the hunting part. Okay, so first, so it also happen if frequency is pulsating. Okay, if it is a supply old frequency where then also causes the hunting. Okay, when synchronous motor, okay, when synchronous motor is loaded and rotates fall back by phase. Okay, if it alpha also increase also, that is another case. Okay, and also torque produce. Okay, if load of the machine, load on the motor decreases, okay, suddenly alpha also change. Means if where is the as we discussed earlier, so if where is the load, the alpha also varies. Okay, if doesn't varying the load means alpha doesn't change. Okay, that thing we work. Okay, so these are so related to the okay, due to the okay, so due to the rotor starts oscillating like pendulum. Okay, so whatever the rotor of the synchronous motor is, it will be oscillate the uh, sides. Okay, so this should be in the axis, but it will rotate the due to the variations. Then it will come. Okay, the hunting disturbance. Okay, so like this, motor is unfixed right position when load is a motor. Okay, if load changes means so it will try to be on the uh, variations in load. Okay, it will cause us to near to the hunting problems. Okay, so we can say that phase swinging or surge. Okay, so here frequency oscillations, natural frequency, mechanical resonance is set up. Okay, so to avoid the hunting process, we have the measuring. Okay, so we can also reduce it by using the different mechanisms. Okay, so we can have the these are the methodologies. Okay, so how we can prevent it? Okay, so prevent the humping, we are using the damperment. So damperment is nothing but the copper slot which are used in the armature. Okay, so that's the copper slot to avoid the hunting process we have discussed. So here means If the rotor, so rotor having the windings. Okay, so these winding along with here these copper bars are fixed. Okay, these copper bars to prevent the hunting. Okay, so here windings are used for producing the whatever the excitation rate. Okay, so apart from that, we're placing the copper bars. Okay, these copper bar reduced. Okay, so preventing for the hunting. Okay, so look like as a squirrel gauge winding. Okay, so this will be in this. Okay, so depend upon we can type of the rotor how we will do. Okay, so in this diagram showing the projected pole time. Okay, so we can place in the how we will get this. Okay, so damper we construct copper bars embedded in face and field force and shafted to both ends. Okay, by means of the wings. Okay, so so this is about the hunting process and how it will be eliminating. Okay, so in the next sessions we'll talk about the methods of starting of synchronous. Okay, thank you all.